Hello friends, welcome to this introductory lecture or the first lecture on mathematical techniques in materials research. So this lecture might be a review for most of you. So what essentially we will be doing is we will be trying to rather revisit some of the mathematical operations that you would have learned maybe starting from your school days. So the main purpose of a course such as this is to enhance our understanding of certain metallurgical behavior or material science concepts by substantiating with certain mathematical perspective. So you would have learned something about, or you would have learned some metallurgical concepts, metallurgical phenomena, material science phenomena, or their behaviors. And what essentially this particular course attempts to do is, it attempts to substantiate that understanding, build on that understanding, view that understanding using, or describe that understanding using certain mathematical techniques or mathematical tools. So that is one of the primary goals of this particular course. So this lecture, these introductory set of lectures, we will try to revisit, like I said, we will try to revisit certain concepts and we will try to relate them to the phenomena, the behavior, the physical side of it that we are interested in. So mathematics can be viewed in an abstract manner. So also we have applied mathematics. So what essentially we want to do is, so far you would have dedicated courses on mathematics, engineering mathematics. So what essentially we want to do is we want to relate that engineering mathematics, the concepts of this engineering mathematics, to material science behavior, the behavior of a material, behavior of a metal. So that is what we essentially intend to do in this course and also in this introductory lectures. So begin with, we will look into a numerical tool, a numerical operation that you might be familiar with and you are familiar with. So this tool you would have come across, or you would have started hearing about this tool, you would have started learning about this tool from your school days onwards. So what essentially we are talking about is derivative. So supposing if someone asks you what is a derivative or define a derivative for me, the classical definition of a derivative that one would render is it goes something like this: rate of change of a function, rate of change of a function, and there is a critical aspect. So the statement has a critical component to it in addition to this, which is with respect to x. So this is generally something rather a description that you get when you start a discussion on when you want to know what a derivative is. However, this course being a research oriented one, I want you to learn ways to express a given concept, a given terminology in an unambiguous manner. So again, since most of the research you will be communicating in the form of written scripts, so whatever you write needs to be unambiguous. It should be able to communicate whatever you have found out in a pristine manner, at least to our best of our understanding, best of our knowledge. We should be able to communicate our research in a clearer way, without any ambiguity, without any confusion. So when you consider this a description for the derivative such as this, when you describe the derivative such as this, a rate of change of a function with respect to x, this statement is not that clear. So there is some degree of ambiguity associated with it. So meaning we don't know what really x is. So when we say rate of change of a function with respect to x, we don't really know what x is. So we want to have a statement that is clear enough to describe the derivative. Again, the reason we are focused on the statement, we are focused on the terminology, because this is largely a research oriented course. So in addition to the mathematical techniques, we will also have some, at times we will also have some discussion on the research aspect as well. So this is how the lectures of this course will go on. So we will be talking about largely, or our discussion will be founded on the mathematical concepts, but when it is required, we will also try to understand some aspects of the research and how to report your research. So this statement that we have here, it has certain degree of ambiguity associated with it because we don't know what x is. So what other way we could derive, or we could describe the derivative, what derivative is, without much of the ambiguity associated with it? How can we do that? So we can say, of course, there is a function, That is, we want to see the rate of change of the function, we want to describe the rate of the change of the function, and with respect to x. So this x is actually a variable that dictates the function. So the derivative, what it essentially tells us is how a given function varies with respect to the variable that governs the function. So this definition assumes that we have a function, and this function is dependent on a variable, and this variable we refer to it as x, and we want to see how this function changes with respect to x. So the whole of the concept of this derivative, the calculus, it begins with assuming there is a function. And for our sake, since we are beginning from the scratch, so for our sake we are considering a simplistic function such as this. So this function we often refer to as the univariate function. The reason we call it as univariate function is because this function is dependent on only one variable. Now, when you want to express the whole of this function as another variable, you can do it in this way. So you can express this whole of this function using another variable, say y. So this y is nothing but the function of f of x. So in this case, what we essentially have is, so this is again a univariate function, but now we have related this univariate function to another variable, and this variable becomes a dependent variable. So this variable is dependent variable, and this variable is independent variable. The terminologies used are here rather straightforward. Y depends on x, so therefore y is a dependent variable and x is an independent variable. Now in the towards the end of the lecture, we will see that it is not necessary that the dependent variable, all the dependent variable should occupy a positions here. Let me repeat, towards the end of the lecture, or in the, when we relate this particular understanding to a material framework, you will understand that, we will try to know that, we will realize that it is not necessary that all the dependent variable should be of a functional form. It should be of the form of the function, and it is not necessary that they should occupy a specific position in a given expression. It is also possible that for us to get rid of a dependent variable and have a similar expression such as these. So here, however, in this case, we have a univariate function, a function that is dependent on a single variable, and we have related that function to a given variable, and we refer to as that of the dependent variable, so that we are able to distinguish a dependent variable from that of the independent variable. Now this expression here, this mathematical expression here, it tells us y depends on the value of y is dictated by x. So whatever value y assumes, it is dependent on x. So the value that y assumes is varied with respect to x. Now the question is, how does the value of y varies with respect to x? So this expression, it tells us y is dependent on x. So as x varies, y also will vary. Now the question is, how is this relation? How is y dependent on x? So when x changes, how does y change? So that is what essentially we gain from derivative. So when we say rate of change of the function with respect to x, what essentially we are considering is how a given function changes when the variable that governs this function changes. So that is essentially what derivative means. And since we are always faced with dependent variable and the independent variable in the framework, derivatives, they play a critical role in understanding the metallurgical phenomena, material science phenomena from a mathematical perspective. We are always associated with, whenever we are studying a specific behavior, whenever we are quantifying a specific response of the material, whenever we are studying how this specific phenomena, whenever we are describing it, we use a specific parameter to describe a given phenomena, and this behavior of this parameter, the change in this parameter, it varies with, or it is dependent on several other parameters. So this parameter then becomes or assumes a role of a dependent variable, and the several other parameters that governs this parameter, they assume the role of the independent variable. So when we want to see how this given parameter, the parameter that we are measuring, changes with this hidden independent variable, we go for derivative. We take the derivative of this parameter. So far we have been just talking about this parameter, that parameter. So let us take an example to help us understand how relevant derivative is to our understanding of, say, material behavior, metallurgical behavior. So one of the behavior that we are often, or we are all too much familiar with, is the phase transformation. So whenever we want to rather manipulate the given property of the material, so one role of a metallurgical engineer is to cater to the needs of the ever increasing or ever demanding technological advancements. So now so what they need is material of a specific property, a material that could render a specific property. So in order to achieve the desired property, what essentially we do is we try to change the phases that are associated with the material, and that we try to do by causing or inducing certain phase transformation. Now this phase transformation is primarily governed by, when you consider the theoretical aspects of the phase transformation, this phase transformation is primarily governed by something called as free energy. Of course, there are different forms of free energy. There are Gibbs free energy, there is Gibbs free energy, and there is Helmholtz free energy. We don't want to get into those aspects for now. So, but nevertheless, the phase transformation that is of desire to us, the phase transformation that we want to establish in a given material, is principally governed by free energy. So free energy is a function, and one of the factors that primarily governs the free energy is the concentration. So now, when you consider an alloy or a metal or any material for that for our discussion, and you want to introduce or induce a phase transformation, you need to ensure that there is an appropriate free energy that is established in the system in order to establish this phase transformation. So when you want to introduce a phase transformation, we need to have an understanding of, when you want to rather have a control over this phase transformation, you need to understand the free energies associated with the different phases. So what essentially phase transformation is, you have one phase that is transforming to another. So when you want to induce this, when you want to govern this, when you want to dictate, we want to have a control over this phase transformation, you need to have an understanding of this free energy. So now here we have expressed free energy as a function of a given concentration. So C is the concentration here. So the free energy is a function that is dependent on the concentration. So far that we are able to understand from this term here. Now we want to know how this free energy changes with the concentration. So when there is a varying concentration, how this free energy changes. So based on our understanding of what a derivative is, then we can take the derivative of the free energy with respect to the corresponding concentration, and this gives us a new parameter which we refer to as the chemical potential. So we began with understanding, or we began with studying phase transformation, and we saw that phase transformation is dependent on free energy, and the free energy is a function that is dependent on the concentration. So the free energy is a dependent variable that is governed by the independent variable of concentration. Now I want to see how this dependent variable varies with the concentration, and in order to do that, I take the derivative of the free energy with respect to the concentration and gives me chemical potential. Now when I say the free energy varies with the concentration, then there is an inherent or implicit assumption that I am making. So when I am saying that this free energy is dependent on the concentration it dictates the free energy, I am making an inherent assumption. That assumption is, supposing I have rather a element or a pure form of a metal, then in this case, the way to represent the concentration, when I want to represent what is the concentration of this metal, then I don't have much of a choice, because this metal is completely made up of a single component. Say for example, if I consider iron, then and when I consider the free energy of the iron, I won't be able to express it as a function of concentration per se, because when I consider a block of iron, entire block of iron is made up of the iron atoms. So all I can do is, when I want to see, or when I want to reduce, or rather reduce the role of the number of moles of, or the number of iron atoms in the material, all I can do is take the ratio of the free energy of iron with respect to the total number of atoms that is present in my given system. So let me repeat, whenever I'm considering a pure metal, a pure form of an element as a system, and now I want to describe the free energy of the system, I don't have much choice. So the only role the concentration plays, or the only role in this case, in this context of a pure metal, the concentration plays is the size of the system. Apart from that, the concentration does not play any role. I'm considering a system of pure metal. In this case, the only role the concentration plays is in deciding the size of the system. Now, with the increase in size of the system, the free energy correspondingly varies. Now, if I want to have a variable, a parameter that is independent of the size of the system, then all I need to do is take the ratio of the free energy with respect to the size of the system. So, the number of atoms that is present in the system. So, when I say the free energy varies with the concentration, it varies, it depends on how it varies, depends on the system. So, I first take a pure form of the metal. So, how it varies, it depends on the system. Now, let us take a pure form of the metal, and in this case, we have a free energy that is dependent on the system only, or it depends on the concentration by virtue of only the size of the system. So, when I say I am increasing the concentration, what I am essentially doing is I am increasing the amount of Fe atom. So, when I keep on increasing the amount of Fe atoms, essentially I am increasing the size of the system. So, in such a system, this is called as unary system. In such a system, the role played by the independent variable in influencing the dependent variable of free energy is quite unique. And now, if I want to quantify what is and how this increase in the concentration in unary system, again, how the increase in the concentration varies my free energy, all I need to do is take the ratio of the free energy for a given system and divide it by the number of particles that constitute the system. Again, this is for the unary system. And when I do that, I end up having a free energy that is for a given set of, or a given number of atoms. So what essentially we as material scientists or metallurgical engineers, we tend to do is we categorize the number of atoms or as number of moles. We translate the number of atoms into number of moles, and we take, now when we translate it, when we have translated the number of atoms to the number of moles, what we can subsequently do is we can take the ratio of, instead of considering all the atoms, we can take the ratio of the free energy that is dependent on the number of atoms that is present, and with respect to the number of moles of atoms that is present in the system. And when we do that, we end up having molar free energy. So this molar free energy is for iron. So since we have considered iron as our example, so this molar free energy is for iron. So what this states is, what is the free energy of 1 mole of iron in a given condition. So you have a system that comprises of 1 mole of iron atoms in a given environment. Then what is the free energy is given by this expression here. So depending on how much mole of iron you have, from this you will be able to estimate the corresponding free energy. So the key takeaway point here is, when we say you have an independent variable and you have a dependent variable, abstractly the rate of change of the dependent variable with respect to the independent variable is the derivative. So when we consider purely a mathematical perspective, it's the derivative that talks about how the change in the independent variable, how the dependent variable changes, we can get it from the derivative. However, when we bring in the metallurgical surrounding to it, when we bring in the context of metallurgy, context of materials into it, then we need to understand what is the dependent variable here and what is the independent variable here. What is the characteristic features of the dependent variable here or the independent variable here. So in this case, when you consider a unary system, here the role played by the independent variable, that is the concentration, is nothing but increasing the size of the system. So as the size of the system increases, of course your dependent variable increases. Now when you want to see how with respect to the increase in size the free energy varies, all you need to do is take the ratio of the free energy with respect to the number of components or the number of atoms that are present in the system. So here we treat the number of atoms as moles, and now when you take the ratio, you end up having a variable using which you will be able to describe what is the free energy of a given system with varying number of atoms present in it. So we begin with free energy in a unary system and we end up with molar free energy that helps us understand what is the free energy of a system that comprises of just 1 mole of iron. So this term in thermodynamic frameworks we refer to, so free energy in thermodynamic framework we refer to it as an extensive variable, and molar free energy is an intensive variable. So whenever you are attempting to understand the derivative of a given function, particularly in the context of materials, we need to understand what is the system that we are dealing with, what is the role that the particular independent variable plays in the system. So once we are able to understand that, once we are able to realize that, the corresponding mathematics will be, rather we can manipulate the corresponding mathematics in such a way that we are able to understand, or we are able to arrive at an expression, we are able to arrive at a parameter that does the job for us. It is not necessary that we have to follow the given mathematical framework. So if we are able to understand the context that we are dealing with, if we are able to understand what we require for a given system of materials, then we can make certain approximation. So here the approximation we made is, we knew what is the role of the concentration, the independent variable in a unary system, because in a unary system we don't have any other additional component associated with it. So in unary system, all the role that a concentration plays is just to increase the size of the system. So it becomes rather straightforward for us now to understand what is the role of the concentration, or how the concentration influences the given free energy, and that role we were able to easily, rather in a straightforward manner, we were able to derive that role, we were able to quantify that role by taking the ratio of the free energy with respect to the number of components, the number of atoms that are associated with the system. So again, it is not necessary that we follow the given mathematical framework. What we can do is, from our understanding of the materials, we will be able to narrow down, we will be able to manipulate the mathematical framework that exists, the generalized mathematical framework that exists, and to address our desired problem. So that is one key aspect of materials research we need to understand. That is, we don't have to directly adapt it, directly use the existing mathematical framework that you might find in a textbooks or you might find in any mathematical works. All we need to do is, we need to understand the system that we are dealing with and manipulate the mathematical framework that exists so that it addresses our specific problem. So in this case, our specific problem was in a unary system. I wanted to see how a concentration of the independent variable influences the dependent variable of free energy in the unary system, and we saw that this relation can be quantified by considering the ratio of the independent variable with respect to the number of components that exist. So essentially what we have here is, we have a linear relation between the free energy of a unary system and the number of particles that are associated with the system. So unary system again comprises of an identical particles, identical number of atoms. So in such a case, what essentially we are doing, when you want to remove this proportionality expression, the proportionality relation here, we can introduce a proportionality constant, say k. So what essentially we have is, with increase in the number of atoms present in the system, we have a corresponding increase in the free energy associated with the system. So that is proportionality that is being written here. So what we have done is we have gotten ourselves rid of this proportionality symbol here by introducing a proportionality constant. Now when you take the derivative of the c, so here what we have n is nothing but c, so this is something similar to having an expression like this. So n is the number of atoms, so that's the reason why we have written it as n. So the number of atoms that is present in the system, we have written it as n. Now it is possible for us to divide it by the Avogadro number, and it is possible for us to express it as something like this, wherein the free energy is proportional to the c. The c is nothing but the ratio of the number of atoms that is present in a system to that of the Avogadro numbers. This will give you c. So ultimately, since our independent variable is c, we can express this relation as this. So that is what essentially we have done is we have replaced the way we are expressing the concentration from number of atoms to the number of moles. So c here represents number of moles. So that is all we have changed. So now the free energy of a unary system depends on the number of moles of that atoms present in that system. Now when we can, like I said, it is possible for us to get rid of this proportionality sign by introducing a variable or introducing a constant of proportionality k. So we have a constant of proportionality here, and we have the free energy that is dictated by the amount of the atoms present in the given system. Now when we take the derivative of this, what we end up having is a constant. So what we end up having is a constant, and this is what we refer to as the molar free energy. This is what we refer to as the molar free energy. So you can take directly the ratio of the free energy with respect to that of the number of moles of atoms that are present, or you can also take the derivative, and ultimately you will end up with a constant, that is molar free energy. So ultimately, for a unary system, the way the concentration, the way the independent variable influences the dependent variable is rather straightforward. So you have a unary system that is made up of a single type of atoms only, and now you are increasing that number of atoms, and you want to see how the free energy of such a system changes. So you have a unary system that comprises of a single type of atom alone, and now you are increasing the size of the system, say from A, now you have increased it to B. Now you want to see how the free energy at A has changed to the free energy at B. So you have increased the amount of concentration, so the amount of concentration now you have increased is Tc, and so the corresponding change in the free energy with respect to the increase in concentration, we have seen it is a constant value, and this we refer to as the molar free energy. Or from this we will be able to understand, based on how much the C changes, we will be able to understand from the molar free energy what is the overall free energy of the system B. So in addition to how the free energy changes, we will be now able to understand what is the overall free energy of the system as well, provided we are able to multiply the number of moles of the atoms that are present in the system with respect to the molar free energy. So this is the unique case for the unary system. What the uniqueness associated with this system is, we have the change in the dependent variable with respect to the independent variable as a constant. So whenever there is a change, whenever there is a, be it increase or be it decrease, whenever there is a change in the concentration, the way the associated free energy changes is constant. So that is the constant that we have arrived at here, because we are largely dealing with a unary system. So we have considered a system that has a specific property associated with it, because we are able to arrive at this expression here primarily because we know the state of the system. We know what sort of a system that we are dealing with. That understanding has helped us narrow down how we treat the given function. So from that understanding, we were able to arrive at this expression, and now we are able to state how the given dependent variable changes with the independent variable. How? The free energy changes with the concentration because we knew the nature of the material. We knew the nature of the system that we are dealing with. So what, from the nature of the system, it is possible for us to state that whenever there is a change in the concentration, the corresponding change in the free energy is constant. So for whatever change there is in the concentration, the corresponding change in the free energy is constant. Now, so far we have been using the term the change in the concentration. We have not quantified it. We have just said the change in the concentration. So how much is the change in the concentration is the next question. When we say it is constant, so how much is the change in the concentration? For how much change in the concentration will the corresponding change in the free energy be constant? So how can we understand this? So we say that for this change, that is dc, there is a corresponding change in the free energy and that is constant. Now the question is how much is the change that we are talking about when we are considering the derivative. Now the way we understand this aspect, how much the change is, often by graphically representing the function that we are interested in. Now let us go back to our generalized understanding of derivative. Let us go to the generalized description of derivative. So here we have y, which is nothing but the function of x, and we have x here. Now let us consider a function like this. So we have considered just a random function. Again we are talking in the context of a generalized understanding. So we are not now orienting ourselves towards a given metallurgical phenomena. We are not orienting ourselves to a given system. We are talking in a generalized context. In a generalized context, we have a function y which is dependent on x. Now we want to see how the x influences y, how much the y changes with respect to x. Now we want to see how much the y changes with respect to x. Now the question is, for what change in x? So we want to see how much the y changes, how much this function changes with respect to x, for what change in x. So often the way we arrive at this expression here, how much it changes with x, is by considering a point here. And when we say change, it is often like it is our intuition to go in the progressive direction, that is to move in this direction. So what we usually do is we want to see, so we have a change in x and there is a corresponding change in f, the function of it. So we have a change in the independent variable, so there is a corresponding change in the dependent variable. So what we now want to understand, we want to quantify that change, quantify the change in the independent or dependent variable with respect to the independent variable. So now it is our requirement to make a change in the x. So now when we want to make a change to the x, one of the easier way to go about is in the progressive way. So we begin by considering another point, that is x plus delta x. So this is x and this is the corresponding function of x. Now we want to see how the f of x changes with respect to x. So as x changes, we want to see how f of x changes. So we move in the forward direction, we move in the progressive direction, and we find another point here. So this point is x plus delta x. So we have x and we have x plus delta x. So meaning the distance separating these 2 points is delta x. Now correspondingly, we have another dependent variable for x plus delta x. So now we start with x. For x, we have a value of f of x. So we have x acting as the independent variable and the corresponding dependent variable value, it assumes f of x. Now we consider another point, x plus delta x, and the corresponding dependent variable is f of x plus delta x. Now here we have change in x and here we have the corresponding change in the dependent variable. Here in this section we have the change in the independent variable, and in this section we have the corresponding change in the dependent variable. Now our ultimate goal is to understand the change in the dependent variable, how the dependent variable changes with respect to the independent variable. So here we have the change in the dependent variable with respect to that of the independent variable. So ultimately, one way of representing this, let derivative which indicates the change in the f of x with respect to x would be something like this. So what we have essentially done is we have considered the function, we have considered it at point x, and now we want to see at point x when I vary the independent variable, how will the corresponding dependent variable will change. So for that we have considered a small shift, we have considered the shift delta x, and with that shift we were able to find out the corresponding f of x plus delta x, and now I have two dependent functions, or rather a dependent variable at two different points which with different independent variables, and I also have the relation between, I also have with me the corresponding independent variable that governs these two dependent variables. So now when we want to see what is the change of the independent variable with respect to the dependent variable, we arrive at this function here. So now these two gets cancelled out, and ultimately what we have is the derivative is nothing but, it can be expressed in this manner as how the dependent variable changes with respect to a change, that is delta x in the independent variable. So what the numerator talks about is the change in the independent variable, and the denominator here talks about the change in the independent variable. Numerator change in the dependent variable, denominator change in the independent variable, and it's same is what we see in our canonical description, in our description for the derivative. So this expression here is equivalent to what we ideally quantify as the derivative. So ideally we say a derivative is, it talks about how a given function, a given dependent variable changes with respect to that of the independent variable, and this expression also allows us to estimate the same. So therefore the derivative can be expressed in this manner. However, it is important for us to note that often, generally for a given function, the way the f of x changes at a certain point, it varies. Let me repeat the way. So let me redraw the same function here in a larger scale. Let me attempt to redraw it on a larger scale. So you have a function like this. Now the way the dependent function of f of x, it changes with respect to x, the manner in which it changes, it depends on x. So if you consider this point x1 here, the way the f of x changes is different from how it changes in x2. So this is often the case. Generally, when we want to talk about a function, we don't know how, for a given point, for a given x, the function changes, how at a given instance at x1, how it will change with respect to x, and will it be similar to that of the x2. So in that being the case, because we don't really know the entire form of the function, in most cases we don't really know the entire form of the function, and in generalized case, without any assumption associated with it, in generalized case, since the change in the dependent variable, it varies with the independent variable. How a given function changes, it depends on the independent variable, not only f of x. Let me repeat, not only f of x, it depends on x, but also in most cases, in generalized cases, how the f of x varies with respect to x, it is also dependent on x. In order to have an accurate estimation of the derivative, using this formulation here, we tend to assume that delta x tends to 0. So this is something that you would have seen if we write it down. So the change in the f of x with respect to x is equal to limit delta x tends to 0 and x plus delta function of the x plus delta x minus f of x by delta x. So this is something that you would have already been familiar with. This is something that you would have learned in your school day. So the reason why we need to include this delta x tends to 0 is primarily because we don't really know how the f of x changes with the position of x. With respect to x, we don't really know how f of x changes. So this change in the f of x with respect to x, it might also vary. In most cases, it varies with x. So in generalized case, it varies with x. So when we want to calculate the change in f of x with respect to x, change in the independent variable with respect to dependent variable in an accurate way using the formulation here, we need to ensure that this next point, the x plus delta x point that we choose, is as close as possible to our original point. So in this case, we have if we consider x1 as our point, the second point that you choose to calculate the derivative should be x1 plus delta x, as close as possible to that of the point that we desire. So now when we do that, so what essentially we have done is we have considered a curve and we want to see how this curve changes. We have considered a function, we have represented in the form of a curve, and we want to see how this particular function changes with respect to the independent variable that dictates it. And now for that, it is possible for us to relate this change in the function with respect to the independent variable. It is possible, we saw that it is possible for us to express it in this way. And now, since we are considering a generalized case wherein we don't know that how this change will occur in a given instant, how this change will be in a given point, we have to assume a small delta x. So because of our, we don't know how this f of x change, or how this change in the f of x with respect to x will change all through this curve, we have to assume a delta x that is close to 0. So if we are focused in this point and we are considering a next point to calculate the change in the f of x with respect to x, we need to choose a point that is much closer to the original point. And when we do that, what essentially we end up having is, if you magnify this here, so we have considered a delta x that is close to 0, and if we choose such a condition, if this condition is fulfilled, if you magnify this, what you end up having is, you end up having a relationship, or if you end up, if you zoom this up, you will end up having a section of the curve that appears to be a straight line. So this section of the curve, particularly this region here, this red region here, that indicates f of x and f of x plus delta x, provided delta x is 0, what you end up having is a straight line. And this straight line is what we refer to as the slope. So this condition for any given function helps us have a straight line at this instant. This condition helps us have a straight line at a given point of any curve. So irrespective of what is the nature of your f of x is, when this condition is satisfied, when this condition, that is delta x is close to 0, when this condition is satisfied, generally the resulting, the change in the change in the function with respect to the independent variable at that point. So in this point we are focusing on the x1. So at this point, this change in the function with respect to the independent variable at this point will be a straight line, and this straight line was what we refer to as the slope. So what we have so far considered is, we have considered the basic definition of the derivative. The derivative, and we saw that it is nothing but the change in an independent, change in the dependent function and dependent variable with respect to that of the independent variable. And we saw that in the context of material science, it is possible for us to have a definite description for this derivative. So when we have a system, a unary system that comprises of a single component alone, then the derivative changes, or it becomes rather straightforward, because the only role the independent variable plays is just to increase the size of the system. So in that case, the derivative assumes a straightforward role. So derivative becomes a constant. because the free energy proportionately, linearly and proportionately increases with the concentration, and it assumes the derivative then assumes a straightforward rule. The derivative is a constant. Now, in addition to that, it is also possible for us to establish or to derive a variable that is independent of the concentration, that is independent of the C or the X in the generalized case. So that we can do by taking the ratio of the dependent variable and the total number of, or the amount of the independent variable that is present, that is the total number of atoms that is present in a unary system. So in that case, we are able to arrive at a variable that is ultimately independent of the concentration. So this, for the unary system, this is not required again for a unary system, because now we have arrived at a constant, and this constant is molar free energy, and this is nothing but the amount of, or the free energy of 1 mole of a specific amount of atoms of a given, in a given system. So this is no longer dependent on concentration, it is a constant like we have seen here. Now moving away, so this is a specific case of a derivative. When we move away from this specific case and when we talk in a generalized term, then we go back to our expression of having a dependent variable influencing, or rather an independent variable influencing a dependent function, and the derivative, which is the change in the function with respect to that of the independent variable, can be expressed using this ratio here. And we saw that this ratio will be accurate when the next point that we are considering is close to, or is separated by, or is as close as the initial point. So express delta x is the next point we are considering. If it is as close as the initial point, only then this derivative will be accurate. So when we say the change in f of x with respect to x, and the question is how much is this delta x, how much is the change in x we are considering, the change in x that we are considering is close to 0. So for a minute change in x, the corresponding change in the f of x is the derivative. So we saw the derivative is change in f of x with respect to x. Now the question was how much change in x are we considering, the amount of change. The one best way of describing the change in the x that influences the f of x is somewhere close to 0, and this is the ideal description of the derivative. So a minuscule change in the x, how it influences the f of x, is what we refer to as the derivative. And if you consider it in the graphical representation, when the change in x, then the change in the the independent variable is minuscule, you end up having a straight line, and that straight line is referred to as the slope. So I hope you are able to rather reorient your existing understanding to certain methodological discussions that we have in this lecture. We will have similar relations, and we will try to relate some of the concepts that you have understood, also that you have learned in your previous lectures, to the concepts in a similar manner. So we will see ourselves in the next lecture where we will try to build on this. Goodbye.